This video is about pandas, the panda apocalypse, and robots fighting off the pandas when the robot pandas
Get out of here! Get out of here! This is my video! This is my video!
There's mustard bombs
Get
involved!
out of here! Alright, so we are here to do the inner and outer radius problem. Alright, so this I showed you guys this in class. This is the weird wizardry one where, remember, the rope was wrapped around the bottom and everybody thought, oh, it's going to go to the left, but it goes to the right because their net force is to the right. Let's do the math and see if it works. Alright, so what forces are there? Well, I've already hold on, I got to finish writing out my givens. So let's see. I've already identified this inner radius is 0.2 meters. This outer radius is 0.5 meters. We're pulling it forwards with this force of 6 newtons, right? Let's see, what else do we know? We know that the mass of the hoop, or the disc, whatever it is 1.6 kilograms. And that the rotational inertia about the center of mass is 0.25 kilogram meter squared. All right, so I know there's got to be friction down here, otherwise it wouldn't roll. I happen to know that the friction is to the left, but you might not know that, right? Okay, so let's just make a note that there's friction, and I don't know which direction it's in. Okay. All right, so I'm going to solve this the same way I always do, which is by writing a net torque equals net torque equation. Am I needed up there? Okay, sorry. All right, so because I don't know this friction force and I don't know which way it points, that makes it a really good candidate for a pivot point. All right, so I'm going to pick my pivot point to be right there. Notice the only other two forces here are gravity and normal force, and about that pivot point, they're not going to produce any torque anyway. All right, so let's start by considering the torque, right, because that'll negate this unknown force. So I'm just going to go just like we always do. We're going to start with one of those net torque equals net torque equations. Net torque equals net torque about our pivot point P. So, I need to do a thing, don't I? Because my rotational inertia is not this, right? I got to use my parallel axis theorem. So let's go over here. Let's see. I about my pivot point is rotational inertia about the center of mass plus mh squared. So h is the distance from the pivot point to the center. So I think it's just going to be the radius again, right? The big radius, so 0.5. So that's 1.6 times 0.5 squared. So when you simplify this, you'll find that the rotational inertia about your pivot point is 0.65 kilogram meter squared. Okay? So I times alpha equals the torque from my applied force. So I is 0.65. Alpha is, that's question A. We're trying to find alpha, aren't we? So I'm just going to leave that as alpha. The reason I hesitated there is because, I guess it doesn't matter. All right, we could have replaced this with A over R, and the R's would cancel. So, all right, so there's our alpha. That equals the torque from the force. Well, the torque from the force is the force, so 6 newtons, times the lever arm. Now, you got to be careful here. Look where my pivot point is. My pivot point is the green dot. The force is up here. So that distance is actually this little missing chunk, which is actually 0.3 meters. Okay? So I can solve for my alpha now, and it turns out to be 2.77 radians per second squared. Cool. So let's make a note. Alpha is 2.77 radians per second squared. All right, cool. So that was question A. And then B wants to know the force of friction. So now that I've figured out that, I can write a net force equals net force equation. So here we go. Let's see. Net force equals net force. So mass times acceleration equals the applied force. I'm going to put plus force of friction. And if I get a negative, that's just telling me that it should have been to the left, right? So this is where I'm going to figure out what direction my friction is in. Before I do anything, I got to find my A, though. A is just alpha R, right? So my alpha is the 2.77 radians per second squared. And then our radius is, well, this point is rotating about the center, so I got to use the big radius. It's 0.5 meters. So if you do that, it gives you 1.38 meters per second squared. Okay, so here we go, 1.6 kilograms times our acceleration, 1.38 meters per second squared, equals the applied force of 6. Sorry, we know the applied force is 6, plus the force of friction. And solve for the force of friction, and lo and behold, it does turn out to be negative 3.78. Oops, 3.78 newtons.
I told you the pandas were invading!
Oh no! Look out! Alright. So that's that one. That was easy. Hey Sally, you want to be in the end of the video? I'm all done. Here, climb up here for a minute. Say hi to everybody. Hold on, we gotta get you a silly hat.
Okay.
You wanna wear this one?
Okay. Ha.
Uh-oh, I can't even see you. Can you be taller? Be taller. I command thee! Uh-oh, we can't see you. Your little face. There we go. Alright, very good. Alright, get out of here, you scamp.
Yay.